Hi there. Thanks for joining us on Space Nuts, where we talk astronomy and space science. My name is Andrew Dunkley. It's great to have your company. Coming up today, we're going to talk water, we're going to talk juice, and we're going to mix it up with graphene. That's it. All coming up soon on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And he's back. It is Professor Fred Watson, astronomer at large. We got off to a quick start today, Fred.
So far, so good. Don't speak too soon. It's very good to see you, Andrew, and I'm sure everything will go flawlessly this morning.
Good to see you too. I meant to ask you something off camera, but I forgot all about it. But you did a little trip the other day in your new EV.
We did, yes.
Now, you were travelling 405 kilometres on a 400-kilometre battery. How did that go?
Look, it was a learning curve, a very steep learning curve, because we've never done that before. Never used a roadside charger or any of the other things. So we stopped about a third of the way in Maitland, your hometown.
My hometown.
We charged the car, but we only added 20 kilometres to it, I think, or maybe 40, because it was a slow charger. So we stopped again at now where was it? Scone. Yes, up the Conter Valley, and ran into a couple who were from Maitland, and they were quite elderly, but I said, "You don't happen to know the Dunkley family, do you?" Told her why I was asking, and she said, "I do know of the Dunkleys. I can't say I know them though, but I do know of the Dunkleys."
Yeah,
we had a nice conversation, but they showed us how to. Well, they sort of helped us, as Marnie fathomed it out, how to use the NRMA fast charger, which solved the problem. And then on the way back, we found the NRMA fast charger in Maitland. So
excellent. Yeah, they're starting to pop up everywhere. They're putting two new ones on the Newell Highway over in West Dubbo at the moment. And they've got two at the Western Plains Cultural Centre as well. And they've got Tesla chargers there and an NRMA charger. But they're just starting to... This is not going to stop.
Hope not.
Given what's been happening in the world lately.
No, that's right.
I'd say, and people have actually said to me, "I'm done with all this. I'm buying an EV." Mm-hmm. I think EV sales are going to skyrocket.
They already are doing. Yeah, there was some numbers I saw the other day, and they're just going up like that. We were kind of ahead of the curve a bit, which I'm very glad, because otherwise we might have been waiting for months for one.
Well, we're halfway there. We've got a hybrid.
Yeah.
But still very economical.
Yes.
Especially around town.
Yeah. No, it's great for country driving as well.
It is, yeah. All right. Yes, brave new world we're walking into or driving into by the sound of it. But not before time, I would suggest.
Well, that's right. Yeah, for the climate at least, that's right.
Indeed. All right, we'll get down to business. Like I said, we're talking water and juice, and we're going to mix in a little bit of graphene, and then we're going to hold our nose and guzzle. But first, let's talk about water, and more specifically, the water that they think is on the moon and how it got there. Now, that's the big mystery, but they're starting to think that it might have been a slow release system rather than one big event.
Yes, exactly. That's right. There's two stories here that have got separate media releases, and they're telling the same story, but
they're also conflicting
with a different nuance. Yeah. So the first one comes from the Laboratory for Atmospheric and Space Physics at the University of Colorado Boulder, and it's about, as you've said, it's about how the water that we do believe exists as ice in the deepest, darkest craters near the moon's south pole. It basically is how it got there, and in particular why it's in some craters but not all of them. It's just in some, and it's the study has basically looked at the possibilities for how the water got there. So the bottom line, there's basically a nice quote here from Paul Hain, who's I think the lead article or the lead author of this. who says it looks like the moon's oldest craters also have the most ice. That implies that the moon has been accumulating water more or less continuously for as much as 3 to 3.5 billion years. And he goes on to say, finding water beyond Earth in liquid and usable form is one of the most important challenges in astronomy. And I think that's probably right. So the mechanism that that they're suggesting, and another quote from Paul Hayne, the mechanism is not quite what you might think it would be, because we naturally, you and I, being space nuts, would turn our thoughts to icebergs, flying icebergs, which we call comets. Yeah. And certainly that's one of the sources that it has been looked at as to how the water got there. They've also looked at whether volcanic activity back in the moon's volcanic era might have brought water up from deep down inside the moon. So all of that, those considerations have been taken into account. But one that you and I might not have thought of is the solar wind, that the charged particles that come from the sun are basically contributing to the water on the moon's surface. And once again, Paul Hayne says, through the solar wind, a constant stream of hydrogen bombards the moon, and some of that hydrogen can be converted to water on the lunar surface.
Wow.
So no matter where it came from, these researchers believe that the ice is sort of built up. And they use the term cold traps. We used to use that in engineering for cryogenic devices, cold traps, which to them are craters on the moon's surface that are in permanent shadow from the sun. And in some cases haven't seen the sun for billions of years. Yep. And they're going to be very, very cold places. And that's where the water has accumulated. One other quote, what's clear is that the ice has a patchy distribution. It's not concentrated in the same quantities in every crater, and they don't have an explanation for that.
Except maybe the age of the craters.
Yes, that's right.
So more water in the older ones.
The longer it's being a cold trap for, the more water it's likely to have.
Yeah, it's interesting that it sounds like a lot of the water's been created on the moon by the solar winds. That's fascinating.
It is, isn't it?
Yeah.
That's right.
Because I was thinking maybe build up over time through meteorite impacts or something, because everything's got a bit of water in it, I guess.
It does, yes, at some level. Most rocks that we think about in planetary geology have got some water in them. Not all of them, but some of them do. So yes, the idea of a single big impact with a comet filling up these craters seems to be ruled out. It seems to have been a longer process.
Well, they've ruled that out with Earth too, haven't they? Wasn't there a study some years ago we discussed that said most of Earth's water probably was already here? It just, in the conglomeration of what became Earth, there was already moisture in the planet. It just took all that time to surface when the conditions were right.
That's correct, and that's because what the studies that have been made of the water in comets seems to suggest that it's, generally speaking, not always, but generally speaking, has got a different isotopic ratio, or ratio of normal water to heavy water, than what we have here on Earth. So that kind of put the boot into the idea that comet bombardment was the thing that actually produced the Earth's water. Or the thing that principally produced the Earth's water. And the suggestion now, exactly as you've said, is that much of it comes from the rocks themselves from which the Earth was made. And so the same thing would apply in the case of the moon.
Yeah. Well, we've seen it with Mars as well, which we talked about the other day, where the water there is not the same as Earth. It's saltier and there's more deuterium in it than on Earth, I think was if I'm remembering rightly.
I think that's right, yeah.
And this other article about the water on the moon suggests that it's definitely there, but there mightn't be enough of it for future need when it comes to, getting on the moon and starting to make rocket fuel and all the other stuff.
All the things, that we talk about. That's right. This is work being done at the University of Hawaii, and they have looked actually at high resolution images from various spacecraft like Lunar Reconnaissance Orbiter, and these are quite new observations, and I'm sure some of the imagery coming back from Artemis 2 will probably contribute to this as well. But what they're saying, from the views that they're now having of these deep craters, that the ice that we believe is in them is a lot more diffuse than was thought to be the case, suggesting that it might not be quite so easy as we've hoped to dig up the water, dig up the ice, turn it into water, and dissociate it to hydrogen and oxygen. And so it is a very important result. They're suggesting there isn't as much as we've really been led to believe. And so these permanently shadow regions, or cold traps, as we were just talking about, might not have as much water as was thought. Part of that comes from some of the earlier missions that, once again, orbiting robotic spacecraft, Lunar Prospector from NASA, Chandrayaan-1, which is an Indian spacecraft. They detected a hydrogen signature, which they interpreted as being due to water ice, but it's suggesting that maybe there's more hydrogen than water. This work from the University of Hawaii. So they used an instrument specifically designed for this purpose that flew on a spacecraft, which I think might still be operational, the Korea Pathfinder Lunar Orbiter, which was launched back in 2022. So essentially, they've used a NASA instrument on board that spacecraft to identify the ice and look for signs of ice, and they think it's quite low, the proportion.
That's a bit of a worry, given what they're planning, like the moon being a jump point for missions to Mars, putting a permanent residential estate on the moon.
Yes, that's right.
That kind of thing. And of course, Elon Musk now thinks he'll go to the moon instead of Mars. So, water is an essential, absolute essential. So if there's not enough of it there to do all this stuff, we're going to have to take it.
One of the comments from the authors of this second paper, the University of Hawaii paper, one of the authors has commented, orbital measurements like those that are reported in the current paper are fabulous in that they can provide broad regional surveys, but oftentimes what you're looking for can only be addressed by in situ, boots on the ground exploration activities. The sooner that we get robotic and human assets on the lunar surface to investigate this particular issue, the sooner we'll have some definitive answers. So there you go. It looks as though we're looking towards Artemis 4 in 2028 to find out whether there is ice there.
Yeah, and it'll also give them a chance to look further into that first part of the story we were talking about, because when they analyse the ice, they'll get more of an idea of where it might have come from. Even if it was locally generated, it'll have a different signature. Yeah.
Yes, that's correct. That's right.
Very interesting stuff. You can read about it at phys.org, Water on the Moon, or you can go to dailygalaxy.com for the second half of the story about the lack of water on the moon, or read the article or the paper in Science Advances. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
The crew of Artemis 2 now bound for the moon. Humanity's next great voyage begins.
Space Nuts.
And Fred, our next story takes us from water to juice. But this juice is not something you can drink because it is a spacecraft. What's really interesting, though, is how they retasked it. This is an ESA spacecraft. They retasked it to do a bit of an analysis on the exocomet that we've seen a lot of press about this year, 3I Atlas. And they've learned some amazing things.
That's right, exactly. So JUICE, of course, on its way to, it's the Jupiter Ice Moons Explorer. It's on its way to Jupiter. And en route, it has passed, not desperately close, but probably closer than we have seen it, past Comet 3I Atlas, the interstellar comet that is still whizzing through the solar system, 60-odd kilometres per second. I'm not quite sure where it is now, but it's certainly on its way out of the solar system. And so observations were made with a camera that wasn't actually designed for looking at the universe. I think the camera that they used is a navigational camera, but it's one that has filters on it that have allowed the JUICE mission scientists to image the comet in different color bands. And what we see is basically new information. It's the fact that there is a very powerful water vapor signature, which you kind of expect because comets, when they get near the sun, they release water as a vapor, and that has its own spectral signature. But what surprised everybody is the amount of water vapor that's being released by 3I Atlas, 2,000 kilograms every second that they're talking about. And that's quite a lot. And actually the ESA article quotes that as being equivalent to 70 Olympic-sized swimming pools every day.
So that's 70 megalitres, basically.
Whatever.
Olympic swimming pool is technically
it's a million litres. Okay, yeah. Well, that's it then.
Yeah.
So it's not entirely unusual. It's something that the comets vary in, but it is significant. And they note as well that something that stands out is the steady nature of the outflow, with a suggestion that even several days after the comet's closest approach to the sun, that emission of water vapor was said to be remarkably consistent, and also, and you might expect this, that it streams pretty well from the side facing the sun. That's what you'd expect. That's where the radiation from the sun is hitting. But they're suggesting that some of the water actually comes from a kind of halo of just dust grains surrounding the comet, releasing the gas as they heat up. So it's giving scientists quite a new understanding of how comets behave in the vicinity of the sun's radiation. And even though this is an interstellar comet that comes from a different solar system from ours, it's how there are many common factors in the way it behaves compared with the way a solar system comet behaves. There is it's trailing a dust tail. Comets tend to have two tails, one made of the gas, one made of the dust, because they behave in different ways. Yeah. The tail is something like 5 million kilometers long, and that's fairly typical, but still very, very impressive. So it's and that will be analysed as well. The chemicals that are in that tail are something else that we'll find out about, and we will know a lot more about 3I Atlas when the full analysis of these data go through.
I suppose one of the most interesting things to look into will be, as we've been talking about in this episode already, analysing the water from 3I Atlas, because this is water from a different solar system. And it'll be really interesting if we can, to find out what that water is like compared to what we know here. It could be completely different, could be so much the same that it'll be spooky. Who knows? Will they be able to find that out, do you think?
I'm not sure that they have enough detail in the observations to sift that image out, because I think you need quite high resolution spectroscopic observations to make that determination. But it's still possible that even, maybe even the Webb telescope, which has the spectroscopic equipment that you might need, maybe Webb could have another look and see what we've got in terms of the mix of normal and heavy water, because you're absolutely right. That will be quite a crucial thing. I think that the main thing about this story is, and it's a bit like Cassini, where you launch a spacecraft and you think you know what it's going to do, and you build it with its instruments in order to do that, and then something really unexpected turns up. In the case of Cassini, it was the geysers at the South Pole of Enceladus that they flew through and analysed, never expecting to have something like that to try and analyse. And likewise with this, the JUICE camera, as I said, it's a navigation camera, but it's given us details that we never expected to see from 3i Atlas. So, and especially when you combine it with the view from our telescopes here on Earth, that gives you, for example, it gives you a really great stereoscopic view of where the comet is. It gives you a very high precision determination of its orbit, because you've got one measurement being made from deep space on JUICE and one being made from the Earth. So you've got this really nice way of triangulating its position. So that's extraordinary as well.
It is. I still can't get my head past the fact that every second it's ditching 4,400 pounds of water, or 2,000 kilograms. I mean, every second.
2 tons every second, yeah.
Yeah.
That's a lot.
It's unbelievable. And just for the record, at the moment, 3i Atlas is 882 million kilometres from Earth and change.
Okay.
So it's pushing on towards 883 million kilometres from Earth.
Yes.
That's it's getting out there. I don't know which way it's going. I don't understand this right ascension and declination. I wouldn't know where to look if you gave me that info. You would. I wouldn't.
I'd have to think about it though, because we don't. We do think in terms of right ascension and declination, most particularly when you're a working astronomer, and that's where you're pointing your big telescope, because that's the only way you can find your objects, by putting in the coordinates. I am a little bit out of touch with that now. It's 8 years since I last did frontline observations on the Anglo-Australian telescope, so maybe I'm getting a bit rusty, Andrew.
I suspect they let computers figure all that out now.
Well, you do, that's right.
Yeah. All right, that is a great story, worth reading, and you can get that from the ESA website, the European Space Agency website. This is Space Nuts with Andrew Dunkley. Oh, no, you can't. No, I'm jumping ahead of myself. I'm one story ahead of myself. If you want to read that story about 3i Atlas, though, dailygalaxy.com.
Hey, that's one of the better sims, believe me. We've had a couple of cardiac arrests down here too, Pete. There wasn't any time for that up here.
Space Nuts.
Okay, let's get to that ESA story now, because this is a fascinating one. We've talked before, Fred, about testing light sails. There's been a couple of experiments. I think they were doing one that fell by the wayside that sounded pretty exciting, and there was talk of sending a small sail-driven spacecraft to Alpha Centauri at one stage. But they're still experimenting with different ways of propelling objects vast distances, because solid rockets or rocket fuel systems aren't going to have enough gas to get very far, basically. This idea, though, might have something. It's a little bit different from the solar sail idea we talked about before. A little bit different. Same concept, but different materials, I think.
Yes, that's right. So, you're quite right about, looking at solar sail propulsion to reach the nearest star. Was the breakthrough Starshot project. I think it's now wrapped up. It was basically a design study to see whether this would ever be possible. Clearly work continues on the idea of using optical propulsion, where you beam lasers at a solar sail. And so this experiment, which is indeed reported by the European Space Agency, it was carried out on one of those flights by an aircraft where the aircraft follows a parabolic trajectory, and that effectively means you're in free fall. It means you are not feeling the force of gravity. You probably remember the NASA version of that is called the vomit comet, because it basically upsets your insides because of the zero gravity. There's that lovely photo I used to show it a lot in talks of Stephen Hawking on the vomit comet, feeling zero gravity, and I don't think he vomited, but for all his major disabilities, you could just see the smile on his face as he experienced weightlessness. Really, really amazing. Anyway, a flight like that has been used to carry out these experiments using graphene, which, as I'm sure you're aware, is basically a single atom thick two-dimensional sheet of carbon atoms with that sort of hexagonal structure. It's incredibly strong, which is very, very counterintuitive, but it's got basically, because it's got this single atom honeycomb lattice structure, it makes it an extremely strong material. So I think what they've done in this experiment, as I read it, is essentially taken little balls of this stuff, this graphene, put them in a vacuum bottle, presumably with cameras alongside it, and then blasted a laser at it to watch how rapidly the graphene chunk will accelerate. In fact, I might just read from the ESA press release, because it says inside a vacuum chamber, a continuous laser beamed on 3 small cubes made of graphene aerogel. A high-speed camera recorded the action through glass tubes. Graphene aerogels are ultralight, highly porous materials that merge graphene's exceptional electrical conductivity with the structural advantages of aerogel architecture. They maintain strong mechanical performance despite their low density. And a quote here, the reaction was fast and furious. Before you could even begin to blink, the graphene aerogels experienced large accelerations. It was all over in 30 milliseconds. Wow. That's Marco Braibanti, an ESA project scientist. And the experiment was called Light-Driven Propulsion of Graphene Aerogels in Microgravity. Yes, and researchers at a Belgian university and the Khalifa University in UAE led the study. So apparently, though, under Earth's gravity, these aerogels hardly moved at all.
Yeah.
But if you put them in microgravity, light propulsion suddenly comes into its own in terms of, as they say, velocity, thrust, and distance. And another finding reported in this piece was the ability to control the propulsion by tuning the light beam. The stronger the laser, the greater the acceleration. The laser pulse triggers a sharp acceleration peak, after which the aerogels slow down. So this is, what they say is, although this is still fundamental science, these promising results using light to propel graphene aerogels in space is not only possible, but remarkably efficient, and that might point to future space technologies. Solar sail propulsion, here we come.
Yeah, sounds like it. Well, we're moving towards 100% electric vehicles on the surface of the planet. Why not, light propulsion off the planet?
Yeah.
The problem is stopping, but they might figure. You could probably create. Let's just go leap forward in time and say, all right, you've invented a spaceship to travel using light propulsion, and then you get to where you're going. You just use conventional rockets to slow down, I suppose. Retros.
Yes, that's right. You would
take a while.
Do that. It would. I mean, the only problem with that is if you try and stop at an object, for example, you zoom off to Alpha Centauri. If the velocity of Alpha Centauri is kind of more or less the same as the Earth's velocity, so that the two are moving in the same direction and speed, then you need as much fuel at the other end to stop your rocket, your spacecraft, as you would have done to take it off in the first place if you hadn't used the light sail. But that might actually be a possibility, in the far distant future, that you carry your chemical fuel not to boost it to great speed, but to slow it down at the other end. It's just that it would need to be a lot, because you'd need to basically reverse all that acceleration you've put into it from the light beam. You've got to get rid of that somehow.
I've been doing a lot of research lately into long-distance, high-speed space travel for my new trilogy, which I'm into book 3. I've been writing 1 or 2 chapters a day, non-stop, Fred. I'm going berserk. While the ideas are coming, I'm writing them down. And I'm reaching that crunch point where I've got to really tie the whole thing together and then put that little twist at the end that I like to do. But in the research I've done, it's really quite complicated to accelerate out of the solar system and then get to where you're going, and timing the slowdown so that you don't overshoot. And the other problem is you can't accelerate too fast, or you liquefy everybody in the spaceship. There's unless, of course, you've got, which is science fiction, inertial dampeners. So,
yes, science fiction inertial dampeners. That's
they do the trick. But it is really fascinating. It's really fascinating to do the research and learn the pitfalls of long haul, high speed space travel. It's not an easy thing to do in reality. When you compare it to what you can do in science fiction, which is anything you like, basically. Anything you like.
No, that's great. Excellent news.
Anyway, coming soon.
So is this going to be a Douglas Adams trilogy with 4 parts to it?
No, it's just going to be 3. Unless I get to a point where I've written enough and go, hang on, there's so much more to. I might. I don't know.
I think that's what happened to Douglas.
It can be like that. There it is. But if you'd like to read about the graphene aerogel solar sail system, you can do that at the ESA website, as I mentioned earlier, or you can read the paper in Advanced Science. And Fred, that brings us to the end of yet another episode. Thank you, sir.
It's a pleasure, and always good to chat about these esoteric things.
It is. We'll catch you on the next show.
Sounds great. Thanks, Andrew.
Thanks, Fred. And while you're online listening to us, jump on our website, spacenuts.com or spacenuts.io. Have a look around. Maybe you'd like to be a supporter. Maybe you'd like to leave a review. Maybe you'd like to send us a message. You can do all of that, or visit the shop, or whatever you like, or sign up for the Astronomy Daily newsfeed. You can do all of that at our website. And thanks to Hugh in the studio, who couldn't be with us today because he was studying advanced science. It gave him an awful headache and he's in hospital. And from me, Andrew Dunkley, thanks for your company. We'll catch you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.